Oh, my Lord.
After this, she will tell us about whether or not formality and reduction commute. First step.
Okay, so thanks a lot for the nice invitation. It's really a pleasure to be here in presence, you know, with human beings, really ones, real ones. So as you can see, I will talk about the reduction and quantization diagram here. In particular, the first step, I will explain you what I mean. So we are really in the setting of deformation quantization. So maybe better, in the case of Poisson manifolds. So let me first tell you a little bit what are the ingredients here. So first ingredient, reduction. So what do I mean by reduction? Maybe not every one of you are actually familiar with this concept. So the idea is that we have a Poisson manifold that is useful to describe mechanics, and you have an action of a Lie group on M. Has to behave well, meaning it has to be proper and free, and allowing what we call a momentum map. Which has to be equivariant. This is what we say, let's say these ingredients together are what we say, well, it's okay, Hamiltonian action. And this is what we actually use to describe symmetries. So what we actually do to reduce our manifold, so really to somehow cut out the symmetries, is that we take a regular value on the dual of our Lie algebra, and then we take the pre-image of this regular value under J. In the case, as I said, of regular value, this is actually a submanifold of M. Even closed and embedded one. And what we can actually do is define a reduced manifold, just, you know, taking this manifold C and counting out the action. So making the quotient with our Lie group. And as I said, in the case the action is nice, this is actually not just a manifold, but is again a Poisson manifold. So we can even describe again the dynamics on it with less variables, of course. So this is what we say reduction. And then what do I mean by quantization, let's say, or formality? Okay, this is a quantization conference, so you may know what quantization means, but let me just tell in 2 words what deformation quantization answer. The question is, given a classical algebra, given by smooth functions on my manifold, the Poisson manifold I have in mind, can we actually find a suitable non-commutative algebra, which is a deformation of the classical one? That's a question. And how do you answer this question? By means of, in the Poisson case, by means of formality, meaning that we know, thanks to Konciewicz, there exists a map from polyvector fields, multivector fields on the manifold to multi-differential operators on the manifold. This is what I call F, the formality map. It's not just a map, it's actually an L-infinity quasi-isomorphism, which is nice because, I mean, maybe you don't know what quasi-isomorphism means in this setting, but what I can tell you is that this property means that you have what you want. We have that every Poisson manifold admits a canonical quantization. Because essentially what you take is from the side of polyvector fields, you have the Poisson structure, which is actually a bivector field. And it's a special one because it commutes with itself, where this is the Cartan bracket. This is what we call Poisson. Well, this is a characterization of Poisson, of the Poisson manifold. And this is the equation that we call Maurer-Cartan equation. On the other side, let's say on the side of multi-differential operators, you have the deformation on the manifold, of the product. So you have your pointwise multiplication, which you want to deform as a formal power series, where MK are by differential operators, and even more, we want M1 to be, let's say, equal to the Poisson structure. So you're really deforming in the direction of the Poisson structure. And then what you want this product to be again associative, as M was, and it is. So let's call it mu. Mu is associative if and only if it's a Maurer-Cartan element. So it satisfies again a Maurer-Cartan equation. So I don't want to be let's say too precise. I just want to tell you that this F connects the Maurer-Cartan elements of these two complexes. So that's why actually this is true. The formality implies that every Poisson manifold that admits a quantization. But the idea here is to investigate the diagram of so quantization in this sense of formality. So we have this map, right? As I showed you right now. But I told you before that also the reduced one is Poisson manifold. So I can give you another horizontal map with the reduced manifold. So you see now, let's say we can conceive deformation the deformation reduction diagram by asking that this diagram commutes. Of course, we have no idea what are these vertical arrows. So let's say the plan today is to discuss about the first one. So this one is what we're gonna discuss today. So the classical side. So what's the idea again is to try to interpret reduction in the sense of multivector fields. So we want really to propose a new reduction scheme for multivector fields. Okay, so really phrased in terms of L-infinity-morphism this time. And of course, it has to be compatible with Poisson reductions, right? So we have to then check it out this. So what's the rough idea? Very rough. First of all, we have to think a little bit. Okay, we have polyvector fields, but we would like to encode a little bit the information of Hamiltonian action in this complex. So what we do? We first introduce what we called, well, this is not us actually, this is, I will say, Boris Tsigan and Richard Ness idea. So the equivariant multivector field complex. So this is denoted like this. And so what is this? It's a DGLA, so differential graded Lie algebra. As I said, encoding Hamiltonian, meaning what? Meaning that if you look at the Maurer-Cartan element in this precise DGLA, what you get is not just Poisson structures. You get Poisson structure which are G invariant, so invariant under the action, and allowing the equivariant moment to map. So these are the Maurer-Cartan elements here. And then we assume our manifold to be written as C cross G star. This sounds strange, but I can tell you it's not a strong assumption. So I don't want to enter too much. At the moment, trust me, it's not strong because the action is proper. That's why it's not a strong assumption. We can do that. And then what we can actually prove is that we do have this vertical arrow. Let me write it better. So there exists an L-infinity morphism not necessary. I mean, it's more general if you just say the action is proper. So the map is now this one. So you have your equivariant multivector fields, and you have a curvature, which is actually, how can I say, given by the fundamental vector fields of your action. And then what you have is a differential, which is given by the momentum map, and then the usual Schouten bracket. So this is the DGLA we're considering. And on the other side, you have this guy. So T poly of the reduced manifold, zero curvature, zero differential, as usual, Schouten bracket. So we could prove that there exists such an arrow. How? So let's say what we did was constructing a diagram that actually how can I say that? And then we compose everything and we get this arrow, right? So how do we do that? First of all, since we have this hypothesis, we could somehow rewrite this equivariant multivector field DGLA, how can I say, splitted as Taylor expansion. So here we have a Taylor expansion. Let me write directly. I don't want to write the whole structure. This I will be more precise. So first, you get a quasi-isomorphism in this direction. So you really have to rewrite your manifold with these two directions. You split everything, and then you have to be careful with the structures, but this is, let's say, easy. And then you need something on the other side. So what we do is essentially use the idea that has been used in the symplectic case of a Cartan model. So meaning you have a kind of inclusion map going in this direction and a projection map in this direction. You will see these are all quasi-isomorphisms. And then, of course, you have to invert in a suitable way this arrow, and this allows you to construct the map that you want. Okay. You have to be the equivariant means that you have add star invariant. You see what I meant, maybe. Where it is? Yeah, here. I mean, equivariant means that it's invariant on the manifold and add star invariant here.
And therefore that forces you that in G star you're acting by the coadjoint.
Yeah. And you will see essentially when you have this splitting of M as C cross G star, the momentum map is just a projection on C.
Mm-hmm.
Right?
Okay, thank you.
So the very easy one.
So what you're looking at, if I understand, it is basically a space of leafwise linear Poisson structures, right? That is your.
You will see, yes.
Yes.
At the end, this is
Okay.
actually.
So this is a very particular situation. I mean,
well,
regarding Poisson geometry.
Yes and no. I mean, in the equivariant case, of course, you have a specific Poisson structure. But when you go, since you have this splitting in C cross G star, when you go to the Taylor expansion, then you have a canonical linear one, and this helps you. This is really the advantage of going to the Taylor expansion.
Right.
You will see. You really have a canonical one. A KKS Poisson structure. Okie dokie. So, where is? Okay. So now let me. No, this was not the position I want. Sorry. Better. Okay. So let's start with some more details about equivariant complex. So what's this? So as I told you, I want to define a complex which encodes the Hamiltonian action, right? So you have your action proper and free, allowing the momentum map. So how can I define this complex? So the idea, of course, here you have a degree. The idea is essentially to take, let's say, you will see somehow polynomial maps from the Lie algebra to polyvector fields. That's the idea, because that's, how can I say, the stuff you have in mind when you think about momentum maps. So how can I write it? I take polyvector fields shifted by 1, and then symmetric algebra. Let me call it something like K, because then I have to sum it up. This is like this, right? To J. Yeah. And this I call I. I don't hear, sorry. At this moment, no. At this moment, no.
Right. Sometimes not, right?
Yeah, yeah. I mean, equivariant complex you can define in general. Yeah.
Like wondering, sometimes her M is C times G star, but I'm just double checking this one is not. Yeah, thank you.
Yeah. And as Miguel was pointing out, when I say here G invariant means really under the two transformations, right? So add star and the action. Okay, and the phi action. So here the differential is 0. If we want to discuss what kind of Lie bracket you have here, what kind of bracket you have, it's good to think about this complex, interpret, as I was saying. So in terms of polynomial maps from G to T poly. So this gives you immediately the idea of the bracket. Again, equivariant under the actions, blah, blah, blah. But now the bracket becomes very clear because you can just, this is the bracket. You can just evaluate it, of course. You can just take the Schouten bracket of the image of this map. So these are now multivector fields. Okay, and how do I interpret now how can I insert the action? You have, of course, a canonical map. That takes an element in the Lie algebra and gives you the fundamental vector field of your action. So you see what you get automatically is a central element. Which means you have a curved Lie algebra. Where the curvature is actually minus lambda. So given by, so you see, you really have some special structure, DGLA with a curvature, where you are encoding the information of the action. And even more, you can say that if you look at the Morer-Cartan element, curved ones, these are exactly G-invariant Poisson structure with equivariant momentum map. So you see, I actually cooked up what I promised. So a DGLA, so a complex where the Morer-Cartan elements are really giving you what you want, the Hamiltonian action. They encode this information. So so we actually have now, sorry. So now we have this object. Where it is? So you see, now we have this object. And I explained you also what is lambda. So, okay. Now we can go to the vertical arrow. We can explain you, I can explain you what do I mean by this Taylor expansion. So second step, Ola. Okay, so now we have really to assume, as I told you, M equal G cross G star. And as I told you, if the action is proper, this is not a strong assumption. You always can find an open neighbor of C that somehow, yeah.
Yeah, probably it's the end of the morning. So that's why I will ask this question. So can you be back a little bit, like just a little bit more, like here, yes?
Here? Yeah.
I don't understand. So you say maps from G to T poly wouldn't be G star to T poly?
Say again, sorry?
Why G to T poly, not G star to T poly? When you
sorry, that's a mistake. Sorry.
Okay, thank you.
Now it works.
Yeah. So the action is actually a coadjoint action and not the adjoint action on the first.
The coadjoint.
Right.
The
okay.
add G star.
Okay.
So,
thank you. Okay.
Oh, this one. And indeed, as I said, now you look at M in this way, and then you're really thinking, what is acting here? How you act here? You just have the restriction of your action to C, and here you have the coadjoint action, right? Okay, so we want to really use the idea of making this Taylor expansion. Okay, how do we do that? So we just use the fact that whenever you have polyvector fields on a manifold of this shape, you can rewrite it in this way. You have the polyvector part. So let me call it I. Yeah. And then you have the C direction. So polyvector in the direction of G star, polyvectors in the direction of C. right? And then, of course, you have, let's say, the coefficients, right? As a usual Taylor expansion. Okay. And then you sum it up. Yes. Equal to K. So that's, let's say, the usual Taylor expansion. Yep. Microphone.
I think I just, there must be a misunderstanding, but you said you count the smooth functions on C extra, so they are not automatically in T poly of C?
Say it again, sorry.
You have T poly of C,
Yeah.
right? And I thought that these multivector field you take the...
I got it, right?
Okay.
Sorry. Okay. So what do we want to do? We want first to define a map that from functions, let me call it like this. From these functions on my manifold. I want to split again somehow, right? So I go to, so symmetric algebra of G, yes, cross functions on C. Yeah. This I can easily define. I just have to take coordinates on G star. So I take a function here, and what I get on the other side is just I just have to derivate the functions in the direction of the coordinates on G. Then I have to restrict to C. So this is just the usual inclusion. And then I have the G part. This is a factor, and then you sum it up. These are just natural numbers. What kind of properties this map have? I can tell you, first of all, is equivariant, which we like. It's equivariant, and then we can actually restrict to invariant ones. No problem. And after restricting, we can show it's surjective. And even more, what we like is we can actually extend to polyvector fields. So on the other side now we have polyvectors on C. Again, we can use the fact that this is equivariant and then extend, sorry, to G invariant ones, to G invariant polyvector fields, which allows me to actually define the Taylor expansion around C. Which is the following. So I consider the map. Remember what I had at the beginning, right? I have to extend now, where this? We have to extend to the symmetric algebra. Well, it's the first page, it doesn't matter, I rewrite it. everything G invariant. Yeah, so you remember this was the equivariant complex. And then on the other side, you have SG star cross the expansion that we found, tensor product, this object. Invariant one. So this is what I call the Taylor expansion. So this was TG. And this is what I call the Taylor expansion. And you see, I mean, if you look at the vector space point of view, this is just a Taylor expansion. So you're not surprised if I tell you that this is actually inherits the DGLA structure. Then it makes sense to say what kind of morphism is this one I just wrote you, the TG star. And I can show you, well, we showed that this morphism is actually a DGLA morphism. Which we like. But we want a bit more, because you remember what we had in mind. Okay, we want to somehow include the information of the action. We want to include the information of the action in the DGLA, meaning you have to take care of this curvature that we defined. We defined at some point, let's see, where it is, this lambda, right? So let's see how and what happens if we actually include this guy. Okay, we have this curvature. Let me rewrite, let's say, in a coherent way with this Taylor expansion point of view. Very easy. And if you see, okay, of course, this is inside T2, yes, G of M. But if you rethink a little bit to this splitting, let's say, then this is just, you see, G star. So this is just based on G star. And then you have the C part. Sorry, the action part. So this is T poly 0 and then G invariant. Okay, what we can say again now about this morphism, how does it behave with respect to lambda, on lambda? This is a corollary telling you, now let me write the explicit stuff. So you have your complex with this guy, the curvature. You remember with the differential given by the momentum map and the usual Schouten bracket. And then you expand, right, with this point of view of the Taylor expansion. Right? And now what do you have? You have now the curvature written in the way I just did, lambda, and the same differential. As I told you, it inherits the same DGLA structure, right? And again, the Schouten bracket. So this is the map I just cooked up. And I can tell you, this is actually not just a DGLA morphism, but it's more. It's a morphism of curved Lie algebras. So it really preserves the lambda. And now let's say back to the question Pierre asked me. What about let's say the structure you have here allows you something like having a canonical element which is a linear Poisson structure, right? You really have a KKS now here. I can even write you. So constant structures of the Lie algebra. And then you have the fundamental vector field. Yeah. So you see, I mean, we have this structure, which is linear. It's really KKS. But on the other hand, it's very interesting because it encodes the action on C and the Lie algebra structure. And this was really not available in this precise form in the equivariant complex. This will help us. Okay, now back to the original question I wanted to solve somehow. So this is the diagram I would like to construct. So I did this guy. So this is done. This is the Taylor expansion. Now I have to take care of the rest. So I really have to cook up a Cartan model. I don't know, I don't remember if I told you already, but I call it Cartan because if you look at the symplectic case, you really have a construction like, remember what happens in the symplectic case. You have the reduction, you can be rewrite in this way, can be rewritten in this way. So this is the inclusion, this is a projection, and then what you essentially do is getting a Cartan model for the equivariant Rham cohomology. And the nice thing in symplectic geometry is that you can actually pull back these arrows to forms. Poisson case, that's not possible. But still, we kept the name because we liked it. So let's see what we can do in this setting. So, chapter 3, the Cartan model. Okay. So, okay, we have this nice guy. Well, let me write directly. What's happened? The manifold in the shape we want. And remember that here you have a special differential given by the momentum map. What's the easiest way to get an inclusion map, which we like and can be somehow, morally speaking, working as a Cartan model? We just compute the cohomology. So we compute the cohomology, and this is what we get. Oh, of course, G invariant, sorry. This is huge. No. Right? It's a cohomology, so meaning that the differential is automatically 0, and you have the same bracket. And of course, you get this inclusion map. Okay, so this is, of course, a quasi-isomorphism of DGLAs. I would say by definition of cohomology. Yeah. Okay, we have this. And now what we can do, I mean, this is nice, but we can actually equip this new complex with differential, which is canonical, but non-trivial. So I call it del. Let me define it. So you have just, well, morally speaking, what you have is, again, you want to include the action, but just in the direction of C. And all the rest is just identity, and you just have to inject in the symmetric part at the base of G. So you see the symmetric insertion of your basis, and on the other hand, you have again identity and the fundamental vector field just of the action over C, restricted to C. Okay, we have a new differential, no problem. This is still a DGLA. Okay, so far so good. So I can actually use this complex, this cohomology, with this non-trivial differential as a Cartan model, and you will see why. So you see now we have this object. But now with this differential. This is what we call Cartan model. And you can tell me, okay, well, why did you add this funny differential? Besides the fact that, okay, I wanted to still include the information of the action. What is nice, I can just immediately notice, is that we have a canonical DGLA map, which I call P. So in the, let's say, moral of projection. From this guy. So let me stress with this differential. To what? To the multi-differential, to the multivector fields on the reduced manifold. So this sounds great because it seems like we actually have these two maps, the iota and the P. We have to be a bit careful now because we have to be careful with all the structures. Okay, first of all, you can ask me, okay, but this map, are you sure this is a good map? P, yes, in some sense, yes, because P is a quasi-isomorphism. Okay, this we like. What is wrong with this? And also, if you go to more Cartan elements, all fine, it's surjective. Good. But we have to be a bit careful because we are connecting the two complexes, but with the wrong differentials. Why? Because you remember what we had here. We had that the I is an inclusion, but here we had that 0. So here we have to be a bit careful. We would like to have that iota is a quasi-isomorphism, or also with respect to that new differential. So this del 1. How can we do that? essentially, what we can do, so we want to iota with respect to this differential, otherwise this is not a model. Okay, and then we remember that actually we have something like a canonical element in the Taylor expansion, the KKS structure. Can we use it? Yes, we can use it because it helps me to define a new differential, a well-defined one. How? Another proposition is telling me that this map as I said, is a well-defined differential. And now, which makes me, let's say, it makes the job, makes the canonical inclusion to become a quasi-isomorphism of DGLAs with this one. Let me write it. Let me write it. So I have now, again, Cartan model. With the non-trivial differential, usual bracket. And on the other side, you have the Taylor expansion with this, let me say, twisted differential. So you see it's a canonical inclusion that is actually becoming now a quasi-isomorphism of differential graded Lie algebras. Okay, conclusion, almost conclusion. Theorem. There exists an L-infinity quasi-isomorphism which works this way. So you have your Taylor expansion. Be careful now with this differential. Going to the polyvector fields of the reduced manifold. Via these two maps that I actually cooked up, right? The inclusion and the projection. Okay. Of course, this is, I don't know how to say, this is not the final stage. We have to go to formal power series, but all I said can be somehow, how can I say, generalized to formal power series, just H linearly, no problem. But you know, I mean, so you have a formal analog of this. The point is that you see, let me rewrite again the diagram I had in mind. We have to make a last tricky step, and then we really get what we want. But let's come back to the stuff I wanted. So we have the equivariant complex with the curvature, and this differential. And we want to construct an arrow going in this direction, where here you have the polyvector fields on the reduced manifold. Zero curvature, zero differential. What is this? Zero differential and Scouten bracket. That's what we want to construct. And then we say that no problem. I can construct this vertical arrow that goes to T Taylor, right? And this is preserving the curvature, preserving the differential. And the bracket. So far, so good. And then I told you, I have this Cartan model. With this new differential, usual bracket, doing what? You project there with P. And then you have this inclusion. But wait a second, I mean, because here I have something different. So what I did is, let's say, constructing an arrow iota that goes to this complex, but with another differential. That's my iota. So how do we do that? How do we solve this? The idea is the following. First, you can tell me, well, if you really want to construct this map that I called R, you have to invert the iota, right? So we need to go in this direction. And then what you can actually do is inverting, because you see, let me explain carefully this part. The point is that what you want to do is eliminating this guy, right? So what you want to do is somehow twisting back. So twisting the differential by minus the KKS structure. But this, unfortunately, has an impact here. And you don't want this. You want to keep the differential here and the curvature here to be zero. So, okay, you twist back, but you have to then rearrange things. The nice part is that when you go, this is the let's say, the most technical aspect. When you go to invert this iota, you can always do that. This is an L-infinity quasi-isomorphism. So by the definition of quasi-isomorphism, you can go back. It exists. Writing it down is something different, let's say. So if you look at the books of Lodé-Valette, for example, this is crazy category language, and you say, okay, I want to have a formula. That's not exactly easy, but I have good students. So they did invert this arrow in a way, in a suitable way that actually kills down again the curvature that you get when you twist back. So they could really find a concrete formula for this inverse using this, I don't know to say, these methods coming out of deformation retracts. So they really looked up at this part of the diagram as a retract, so with homotopy. And this helped to really invert this iota in the way that kills back the curvature. So you really have, at the end, you really have the twisted curvature and the twisted structure here, the reduced one, again to be zero as you want. So this is, as I said, the most technical part. But I just want to mention this. It's not automatic. It's not easy to really have the correct differentials in this diagram. But at the end, you can do via these techniques. Okay. So I think I will stop here. I can comment. Well, last thing I can comment is, of course, what I told you at the beginning. So you have a Marsden-Weinstein procedure for reduction, right? And we rewrote the reduction in this funny scheme of L-infinity-morphism. What you can check is that if you now re-look at this diagram and you try to, how can I say, recover more Marsden Weinstein reduction via this R, you can. This is actually coherent with the classical reduction theory. I think I'll stop here.
Thanks a lot. There's a question.
Martin.
Yeah, thanks a lot. Of course, there are two questions.
Mhm.
One, the big and great Stefan Waldmann said last week that dual spaces are evil. And so there's just a cosmetical question. So if your G was infinite dimensional, could you then rewrite, usually one is too lazy to do this, everything with HOMs from G to something else, such that this all makes sense. So instead of writing S of G star tensor something, you write HOM of S of G to something. And or do you, for some reasons, you really need that G is finite dimensional?
I would say yes. Exactly.
Yeah, but the
exactly.
basis, no. This is just the identity map if you write it correctly.
Yeah.
It is just, the map from G to the vector fields, mapping the elements of Xi to the fundamental vector field. It is written in this form to make computations, but you don't have to.
You don't actually use it. That's true.
Mm-hmm.
I was thinking, if there are issues about the action.
But don't worry. I mean,
I don't know. I don't know. I will try to think a little bit. I don't know.
The second question was there must be a relation to what is called BRST or BV.
Yeah. Well, you can actually try to reformulate. This is not exactly automatic to move to the BRST setting when you use this formality language, but this somehow can be done, and this is part of Andrea's thesis, the comparison with BRST formalism. BV, I have no idea, to be honest. Maybe yes, but I have no idea. But BRST, yes, you can definitely reformulate a little bit, because this is, if you think, essentially is coisotropic reduction, right? So, and then of course you go to BRST automatically. So yeah, you can do that. I don't know if this is, in some cases, this can be useful. We also try to rethink a little bit to Fedosol construction in that way, but this is still a little bit unclear, let's say, how to do that. But yeah.
Thanks.
More questions up there?
Yes.
Okay, so my question is, this coisotropic reduction was extended by Marco Zambon and Cattaneo for more general things like to group actions or things like that. Can you do the same in that?
I don't know, to be honest, because you really need this technology of proper and free. So I don't know if this generalization actually works. And I'm not sure you can actually use the same idea of the Taylor expansion. This sounds complicated. We can try, but sounds complicated because we made heavy use in some sense of the fact that you have this kind of well-behaving action. So this, I don't know.
And the second question is, well, at the beginning you write the diagram. So there is the quantum part. What can you say?
Yeah, the quantum part is still working. project. You mean this one, right? The differential operator part. Now, this is still at the very beginning, I would say. I mean, of course, you can reuse many things of the ideas that we had cooked up, but there you have to go more into the direction of using the universal enveloping algebra acting now on differential operators. And this is still a bit more involved, let's say. But yeah, I mean, that's the plan, let's say, to solve also this vertical arrow, which means we could then investigate the commutativity of the diagram. Yeah, but this is, yeah, that's future. We started, but we didn't manage yet.
Okay, thank you.
Are there any further questions? Here in Freiburg, I don't see any more questions online. Also, everyone is happy. So let's thank Chiara again for a very nice talk. And we're now heading to the lunch break, and we will resume at 2 p.m. local time.